So, let us now discuss a little about the martensites. As you know, martensite is one of the important constituents of the quench steels. So, therefore, it is important that we understand how it forms and whether we can control it. As I told, martensites actually are formed during rapid quenching of the steel, plain carbon steel or alloy steel, in all cases it happens. So, in the steels, martensites forms like a plates or laths, and as you see here on the optical micrograph, these grey color features are basically martensitic laths. In between white thing is basically written austenite, written gamma, and we term martensite, as I told, as alpha prime because it's same as that. Now, most of these martensitic plates, they start from one of the grain of austenite and extends many cases to the other grain boundary. So, that means they are pretty long and they has a shape of a lens, just like this, and because they are lenticular shaped and they have finite thickness. So, they are termed as a laths of plates. But question is this, how this transformation happens when steel is quenched from the high temperature to water. Obviously, as I discussed, this is an diffusionless transformations. So, atomic movements basically occurs because of the application of the shear forces, and but this is not so simple as you observe. Okay. As you see, there are plates in the martensites, and let us first look at how the driving force as play for the transformations, then we will get back into the crystallography of martensite transformations. You clearly see here, this is the left hand side, the C portion of this view graph, which is directly taken from Porter Sterling book, shows the relevant portion of the phase diagram. As you see, this is the eutectoid temperature known as A1 temperature, and the gamma phase and the alpha. And by doing proper thermodynamic analysis of martensites and the gamma, because the transformation is from the austenite to martensite. So, therefore, if I plot the G versus temperature curves as a function of temperature, G versus temperature basically, for 0.8% carbon steel, they look like this. As you see here, above a temperature T0 at which both the curves actually intersect each other, the gamma is more stable, and below this temperature T0, martensitic more stable. So, that means below T0 it is possible to transform gamma to martensite, and so it is possible to do the similar analysis for all the steels of different carbon concentrations like 0.1 to about 1.4%, and then we can obtain the T0. T0 corresponds to the equal free energy points for gamma and the martensites, and that can be plotted. And if I plot that curve, it will look like this, as is shown here by this T0 line. So, that means below T0 martensite formation is favorable. Why? Because finite driving force will be available for austenite to martensite transformations. Above T0, that driving force is not available. As you clearly see that the temperature of T0 is basically strongly dependent on the carbon concentration. As the carbon concentration increases, T0 goes down. That means the chances of formation of martensites requires quenching to a lower temperature for higher carbon concentration steels. That is very clear, because T0 is the temperature at which both these gamma and the alpha prime, that is austenite and martensites, have the same free energies. So, but it happens that in many cases it has been found that even if you cool it down below T0, martensite transformation does not start, because martensite transformation requires strain, because austenite to martensite transformations, as I told in the last class also, will develop plastic strain, twinning or dislocation mediated plastic strain, and therefore, even below T0, the amount of chemical driving force available may not be sufficient enough to cause the transformation to happen. And that is why, as you see here in all these diagrams, even a few of the diagrams you will see later, that there is always two important temperature lines shown. One is the MS, other is MF. MS stands for martensitic start, MF stands for the martensitic finish temperatures. So, here the martensitic start temperature is at least 50 to 80 degrees Celsius lower than the T0 temperature for all carbon concentrations in this range, and MF is obviously much lower. But remember, there is very little chance, or in fact there is no chance, let me tell you very clearly, that all the austenite will be transformed to martensites even if you quench directly into liquid nitrogen. That possibility is very rare. The reason I told you earlier also, because with strain development the chemical pH is taken completely consumed by these strain, and then there is no driving force available for the further transformation to happen, and this is the reason some amount of austenite is retained in the microstructure. And one of the ploy people use in the industry to avoid retained austenite is to quench many times, so that the austenite can be further reduced in the martensitic steels. Okay, so what is the exact diving force? That is shown on the figure B. You see here for as a function of carbon concentration, here again you see this is for the alpha, okay, alpha prime, basically this one, this left hand side curve, and right hand side curve is for the gamma, and therefore if I have a certain concentration C0, the distance between these 2 points is basically what is known as the diving force available. Reason is very simple, that this is the equal free energy point. That means the point at which both the free energies of the alpha and the gamma are equal, and this is the common tangent between these two curves. So, therefore, the common tangent will tell you the equilibrium between two curve phases, and therefore, this distance is what is marked as delta G as a driving force available for the free energies for the transformation of the austenite to martensites. We will come back to this part D later, because that is about the TTT diagrams, okay, but it is very clear that this martensitic transformation is slightly different from the any other transformations. So, that is for the diving force with transformations. Now, let us see what actually how the transformation happens. This picture is also available in the books of the Porter and Sterling, but I have taken this picture from one of the websites known as slideshare.net. As you see, the martensites has a body centric cubic structure. I have been telling you again and again, it is a body centric cubic structure. On the other hand, the parent phase austenite is a FCC structure, and this is a very simple way to generate these body centric cubic structure or body centric tetragonal structure rather from the FCC unit cells, and this was done by E.C. Brain long back. As you see, this is the construction, the top part, the FCC austenite is shown there. FCC austenite is shown by x, y, z. You see here, this is the coordinates, and the coordinates of the martensite is shown by x prime, y prime, z prime. Obviously, if I have two unit cell or FCC austenites sitting side by side, we can simply join the points like that. Okay, we can actually connect the atoms like that here also at the bottom, and you can get the BCT unit cell this way. If you do that, you will find that there is actually 20% contraction along the C axis, then along the Z axis basically here, and about 12% expansions along the axis. That is what happens, and one can actually do the crystallography very easily. If suppose this is my this is these FCC austenitics unit cell, that is what you see here. FCC austenitics unit cell has a lattice parameter of A0. Now, obviously, the C axis will remain as A0, but other two axes will become A0 by root 2 or A0 by root 2, because they are the half of the phase diagonals. That is what is shown. This is the whole phase diagonal, so I am taking half of that. So, but if I simply taken bodies FCC iron unit cell and do the same analysis, obviously there will be no change, no expansion or basically contraction on the C axis, obviously, because iron atoms have similar sizes. There is no distinction of the iron atom sizes when it is quenched from FCC to BCC structure or BCT structure, obviously, because they are all similar sizes. The moment you have carbon atom in the steel, this carbon atom actually goes and sits in this position. You see here, these are the marked positions of white with black dots. That is where the carbon atoms are sitting. That is, they are sitting along the that is 001 directions. All the 001 directions will be occupied by the carbon atom at the central positions, and these are the atoms which undergo shuffling, or rather these are the atoms they undergo basically movement during these transformation of austenite to martensites. So that is one important part you have to remember. It is not the iron atoms which are undergoing shuffling or movements because of these transformation. Only the carbon atoms were small enough, so they are easy to move by application of the forces. Now, so therefore, if I draw the whole unit cell, let us draw it here. If I draw a large number of unit cell, okay, let us draw it that I am not going to draw atoms. I am only showing these unit cells here to make it clear to you. Okay, so it is very clear that this transformation can easily happen along these things, zones. So if I draw only 3, okay, now I can actually generate these unit cells very easily. Okay, this is the unit cells, you can clearly see there. This is one BCT, this is another one. Okay, this is the way you can generate many unit cells. Okay, this is another one, like that way you can generate. So what is the moral of the story? Moral of the story is very simple, that if I want to transform austenite to martensites, what I need to know, I need to simply basically connect these unit cells and just move little bit. So it's just like a chain reaction. The cells get suppled up. Originally aligned FCC unit cells, actually simply get suppled off because of these situations. Okay, that's what happens. They are actually getting shuffled up. That means they are like a pack of cards. You are rotating them to the directions to make this BCT unit cell possible. That is how actually transformation happens, and it has been found that transformation happens at the speed of sound in the steel, because it requires only distortion of the unit cell a little bit. That is what is required. As you clearly see that this is just like a bend created from the originally aligned FCC unit cell. So that much distortion is required to generate BCT structure in the martensites. Obviously BCT is mainly because carbon atoms are going along these 001 directions of the BCC unit cell, and they are the ones which are leading to the contraction on the C axis and the expansion on the A and B axis. Okay, so that is the main reasons why BCC become BCT structures. But as I told you, the C by A ratio, that is the tetragonality, is very small in case of martensite. It is not very high. So this is also understandable because carbon atom is small, very small in size. So therefore distortion it creates along these 3 axes will be not very large amount to make the C by A ratio distinctly much different from 1. Okay, so in a pure iron, after martensites, there is no difference between the lattice parameters. A remains A, B remains B. Is okay. The only thing it changes is basically these things become A by root 2. Okay, so that's the difference between because of the carbon atoms. So carbon atoms actually obstructs, as you said, the contractions. Okay, although this contraction is required, but they sit in such a way that the lattice invariant of the construction, the obstruction happens. Fine, so you don't need to understand all those complex stuffs. Only thing you need to know that it basically happens like a pack of cards in a steel metallurgy. It's very easy to do this transformation. That's why simply by taking a steel and heat it at high temperature and quenching into water, immediately transform it to martensites. It's very easy, and this is the reason why it happens. Now this is a detail of that. Basically it's already there in the books, so you can actually look at it, these different directions of the crystal. So that is very easy to understand that because martensites is forming just by sharpening of the unit cells from the FCC austenite structure, there must be certain planes which will be parallel to each other. There must be certain planes like 1 1 1 1 1 planes in the martensite austenite must be parallel with 100 planes, sorry 110 planes of martensites. Similarly, some crystallographic directions also will be parallel to each other. So depending on the type of steel, people have observed different orientation relationships, and that is crystallographically they are related. So those plates which you see, they are actually not exactly completely invariant with respect to the austenite. They are having distinct crystallographic relationship with the austenites, and that's obviously understandable the way the transformation occurs. Okay, now let us look at, if I have to consider 2D. Okay, as you see, the martensite looks like a ellipse, okay, or basically looks like a, in a 2D there looks like a ellipse. How this ellipse actually happens from a circle? That is why the distortion actually can be explained. So if I plot only one section x z, okay, y is shown as a extra axis, but it's on the, not on the plane, it's actually other side of the plane. Now if the original circle which is shown here is by this one, this is a circle. So simply by shuffling the unit cell, what is happens? You will see that along all these x, z has contracted and x has expanded and y also have expanded, okay. But there is a direction you clearly see a written AOA, along that there is no distortion happen. Simply this one also, you see, let us write A prime, and this is A, and this is also A prime. So A prime, along these two directions there is no change of this length, that is the radius of the circle. Radius of the circle remains same, and this is observed in the real martensite structure. That means what? Although we are talking about the distortion and the shuffling of the unit cells from the FCC to BCT structure, during martensite transformation there has to be a plane which will not at all undergo any distortion. That plane must exist in the martensitic structure. As far as this construction is concerned, if we have to retain this such a kind of this deformation during transformation, this plane must exist. This is known as lattice invariant plane, the plane which has not undergone any kind of distortion or deformations. Okay, that plane will exist in the martensitic structure. Okay, let me see whether I have such a kind of picture or not. Okay, may not be there. We will come back to it later. So this is the unique feature of martensitic steels. Although the cells get shuffled up or distorted from the FCC to BCC structure, there will be a plane which will remain undistorted, and that plane is present in martensitic structure. So that means what? Distortion will happen in such a way that negative and positive part of the distortion will cancel out along that plane, and in martensite that plane happens to be 110 plane. So 111 plane in steels, 110 plane, basically 110 plane is basically undistorted plane in the martensitic structure. Now how this exactly happens in the real sense, like a pack of cards, is shown here. Okay, you see this is the austenite, this is the martensites. As you know, let us look at first from this A to A. Okay, so as you clearly seen, this is my case, and if I want to create a martensitic structure, what I am doing? I am basically creating such a kind of a distortion, right? The whole thing which was lying like a nice structure. Okay, I shown you again. Let me show it using the 2 unit cells. Oh, okay, let me draw it here. It is easy always to show 2-dimensional way. It is always difficult. Okay, so I am showing it here itself. So this was the 2 FCC cell, let us suppose, and we generate such a kind of a martensitic bodycentric cubic structure. Okay, that's there. Let us assume. So we can actually consider these in 2D like one I have drawn. Now, in order to keep one of the plane lattice undistorted, what it will do? It will simply retain the plane undistorted. You see here, this plane is written undistorted. These are this plane, parallel plane, written undistorted. What it has done? It has it has basically created a step here like that. You can see here. This is how it has distorted. It can be produced. So distortion happen like that way. Correct. So, or in a little bit more visual way, you can see here, this is how the distortion happens. Okay. So by doing so, you are creating internal twins automatically. So in order to keep that undistorted plane remain to be undistorted or undeformed during transformations, this twinning must be done. The twinning is a process by which this plane can be retained undistorted. So therefore twinning is very paramount importance in the martensitic transformations. And we have seen in the last class also the twins are basically present in all the martensitic structures, martensitic plates, they will be present. So that means what? This is just like a shuffling of the cards. I am distorting the cards one by one like this way. Okay, one, this, then this, then this. That is how it happens in the real sense in 3D structures. 3D will be a little bit difficult to understand or conceive. That is why in the books also this is shown in two-dimensional way how this can happen. Okay, and yeah, just then comes the 3D. Okay, now in 3D, this just like that. You see, these are initially all the cards were lying on the plane. Now what I'm taking a card up and putting like that. Again, I'm making a step and taking a card up, putting like this. So just like that, I take a card up, put it like this. So if I want to keep it like this way with a certain angle, okay, that's what is shown as here. This will lead to a twin. Now two different configurations are shown here. One is there as the card is taken up. So initially it was a circle lying on the plane, and as you take the card up, so this will get distorted just like a ellipse. Okay, this is a twin one. On the other hand, the one which is present on this plane, this is the one. Okay, that's also get distorted in another way. So that's actually in 3D way you can create two sets of twins, two sets of actually twins, which in 3D, 2D you have seen that there is only one set of twins. In 3D you creates two sets of twins to keep this on the plane undistorted. And this reference plane, which is basically shown as basically for the FCC structure. And you see, this is what is known as the habit plane, or the plane which has not undergone any kind of distortion. Okay, so keep that habit plane intact. These twins have to be created. And to show you that twins do exist, okay, one can do crystallographically also. One can show that this is the twin, where this is the twin configurations. Okay, let us not go into this. This is a three-dimensional twin relationship among the different martensitic variants. That's let us, for the time being, let us not discuss about that. And I showed you in the last class also that how the twins exist. You see that internally these twins exist inside the plates, and so therefore it is same thing like I shown you. Okay, this is just like a pack of cards. Okay, you see if I draw it here like that, so there is this distortion happens. Okay, this is the way things happens. Okay, so there is a distortion. So initially this was a flat thing, then you are distorting up. These are visible when it is observed under transverse electron microscope, and in transverse electron microscope things are actually projections from the original picture. So therefore you do not see these orientations nicely, but one can actually do better imaging to show that at the end of the plates these twins are aligned at a particular angle. They are never actually on like this, they can never be like this is not allowed. They will be always at an angle with respect to that. That tells you how the pack of cards can arrange themselves. The one thing which I have shown you earlier, this picture, or even this picture is better. Okay, so that is how actually things happens. So martensites have a distinct crystallographic feature which is completely different from bainites or pearlite, and that makes them completely unique in terms of the microstructural features. Important thing for you obviously to understand the transformation, other than that to detect martensites in the microstructures. As you have seen, most of you when you look at martensites in the steels, many cases you will be confused with the bainitic plates, because bainites and martensitic plates looks almost similar. Okay, many cases, especially lower bainites. But in martensite there is no carbide phase. Let us be clear about it. Martensite has a unique supersaturated body central tetragonal structure. There will be no carbides presence at all, because all the carbon is supersaturated in the body centered cubic structure, body centered tetragonal structure rather. Okay, so that is the unique difference. Other than that, as I told you, martensites plates will be appearing like these. You see here long needles or elliptical separate plates. This is clearly visible in a optical metrography, and it is better actually to do optical metrography than scanning electron microscopy on the martensites. Unless until martensite plates are very fine, which is not very rarely observed. Martensite plates will not be so fine that it has to be seen under the SEM, but they are normally observed in optical martelograph, very micrograph very easily. Okay, so that is the important part of martensites, and as I told you, I discussed you most of the features, and this one also I have discussed. And so therefore upon knowing all this stuff, it is important that we should also know how the martensitic nucleation happens. See, martensite's nucleation, as I told you, in the books also they have given. Let me just read out the books. That particular portion is very interesting part. Okay, a single plate of martensites in steel grows in 10 to the power -5 to 10 to the -6, 7 seconds, just like a microseconds, to its full size at the velocities approaching the speed of sound. Using resistivity measurements to monitor the growth of the individual plates of martensites, especially in iron nickel alloys, it is found to be 800 to 1000 meter per second. That is done by Nishiyama et al. So that means what? Growth is rapid. It is just like a blink of eye, the martensite plates grows from one part of the grain to other part. One important aspect is the nucleation. Okay. And now nucleation of martensites is distinctly different, it is not same as we can think about it. Okay. So that nucleation will just discuss in the next class a little bit about it. Obviously to discuss nucleation of martensite will take a separate course altogether, because first of all let me clarify it, in the books or even in your courses, teachers will never say that martensite can nucleate. In fact, I still remember my days when I was just studying my bachelor's. If I tell that my teacher has told that martensite transformation involved a nucleation, people used to laugh at me. Okay, but even in the books you will see there is a particular portion, theories of martensitic nucleation. Okay, that means what? Nucleation is evidently more important in Martin transformation than the growths. Very clear, because the growth happens at such a high speed. It is just like a almost like 800 to 1000 1100 meter per second, is extremely high in a small sample. So that means what? In a fraction or in a basically microsecond, the whole transformation is finished, done. That is expected, because we are quenching the steel from the high temperature to the water, immediately everything will be over. And that was actually happened to Martens, who discovered this phase. So that, as I told you, the reason we discussed the growth or the crystallography or things is that Martin transformation involves shear, that is the plates gets arranged in a different manner. So therefore there is a involvement of the shear forces, which leads to basically shuffling of the plates, shuffling of the atomic planes. So this strain has important role to play in martensitic nucleation. Okay, and that's why the martensite transformation requires cooling down at least 50 to 80 degrees Celsius below T0 temperatures, as I discussed with you. That is the reason, because the strain which is built up, because to start the transformation is to be taken care by the excess chemical driving force, or the basically chemical free energy difference between the austenite parent phase and the product phase martensites. That is what is important. Okay, so let us discuss in the next class, that will be clear to you.